There are hundreds of billions of stars in our galaxy, the Milky Way. If you counted one per second, it would take you 30 years to get to 1 billion.
Hipparcos, the world's first astrometric satellite, was launched by the European Space Agency on the 8th of August, 1989.
We were able, with Hipparcos, to get information about the distances of 100,000 stars. Those stars were very bright and very close to us, very nearby. Our knowledge of the galaxies was limited to a small surrounding of the Sun.
A decade after the launch of Hipparcos, the European Space Agency embarked on a much more ambitious project, Gaia, the billion-star surveyor.
Hipparcos produced an accurate map a few hundred parsecs around the Sun. Gaia will extend this over a much larger volume, covering basically a quarter of the whole disk of the Milky Way. It will also it will measure for bright stars, in fact, all over the Milky Way.
Gaia is measuring 1 billion stars.
Now we are going further and further.
3, 2, 1, top, décollage.
The step that is made in those 20 years to me is absolutely unbelievable.
But it's not only making the star map of the sky, we are measuring the distances and motions to the stars. We are measuring a position of a star with half-year difference, and the movement of this star, which is not a true movement, we can deduce the so-called parallax angle, which gives us, through trigonometry, a handle to the distance. Unfortunately, things are a little bit more complicated. It's not only the parallax, but the stars are actually also moving.
In fact, Gaia observed the object many times during this mission. You observe at the star at the beginning, and you reobserve it, reobserve it, reobserve it, and you see its motion. It's because the precision of the Gaia mission is very good.
The angles that are involved are extremely small. If you imagine a euro coin, which is about 2 centimeters in size, and in the case of Gaia, we go down to about 10 micro-arcseconds in accuracy. And that means that you could even see this euro coin lying on the moon.
We know that all the stars are moving, but to have information about how they're moving will give us information also on the way in which our Milky Way was formed. It can tell us how many stars comes from outside our galaxy.
Every day from space, Gaia sends about 40 gigabytes of data back to Earth. The data is extremely complex. A huge human collaboration is needed in order to turn it into the map of the galaxy that astronomers have been waiting for.
Globally, Gaia is doing a 3D map of the galaxy, but not only, it's also measuring the brightness of the objects, the colors, and for a subsample, the radial velocities. And this is a very complex task, not only because it's a vast amount of data, but also because of the interwinding of the data. So from the same photon, you derive several different information. And this, you have this interconnectivity of the data, and that makes things difficult. At the level of the consortium, I think now we are probably about 500 people. Such a project, it's more than a quarter of century from the first proposals. So you have an effort which is enormous from many people on a long term. But we see that Gaia has, through the first data release, a huge impact in many different topics in astronomy.
All the people that we start working on science with Gaia, they maybe will know a word that we have never seen before.
This data set in itself would be enough for decades of work. Gaia is a mission that continuously scans the sky. It looks at everything that is bright enough for its telescopes, every point source. That means it also measures objects in our solar system.
The idea is that at the end of the mission, Gaia will observe 300,000 asteroids and it will change completely our visions of the asteroid belt or of the nearest asteroids as well.
When the archive is opening, then there will be various kind of people looking into the data. There are clearly astronomers who have their favorite star, and they can know what is the distance to it. But there are also people who are interested in certain types of stars, and then they want to look the whole sky.
In the second data release, we have more than 500,000 variable objects. Gaia will discover many of these new variable stars, and we hope that we will detect a new variable type.
It's going to change completely the way in which we look at astrophysics now, in very many fields. So it's going to be really a revolution.
From 1 billion stars, of course, there will be a few completely new type of objects that we will have to discover and to understand what they are.
After Gaia, we will never look at the night sky in the same way again. Are you ready to explore our galaxy?
After its launch in December 2013, Gaia began a 5-year mission to scan the skies and map 1 billion stars in our astronomical neighbourhood, the Milky Way galaxy.
Our first release will contain positions of 1 billion stars. So that will allow us to look, what does the night sky really look like when you would look at in random direction with a telescope which can see very faint stars. And a subset of 2 million stars, we will have the distance and the motion. So that is really the basis for astronomical studies. People can really look into details of these sources and study the behavior of the stars.
In addition, Gaia has produced light curves for about 3,000 stars, showing how they have been varying over time. And this will help scientists better analyse the star's internal structure. The first satellite to chart the motions, positions and distances of stars was ESA's Hipparcos satellite. That was for about 100,000 stars. Gaia's task of pinpointing the position and movement of 1 billion stars is unprecedented and will help answer questions about our galaxy's structure, how it is evolving and how the stars reach their current positions. To do this, the spacecraft is orbiting around the L2 Lagrange point. The Sun, the Earth and the Moon are all roughly in one direction, and the sum of gravitational forces makes it an ideal position to study the stars at the dark side of the sky. After various technical issues were resolved, Gaia is operating at full capacity, continuously performing science and collecting data.
Well, the big challenges are the size of the focal plane, which is roughly 1 meter by 60 centimeters. It's really big, it's 1 billion pixels. The accuracy with which they scan the sky, that has to be very stable. And then the positional accuracy, we want to get down to 10 microarcseconds, and that means roughly the size of a coin across the Atlantic.
All the data from the stars is transmitted to Earth using ESA antennas on the S-Track network in Argentina, Spain and Australia. From there it goes to Darmstadt in Germany, where the spacecraft is controlled, and then to an ESA data processing centre in Madrid. The next step is to distribute the data to specialised data processing centres across Europe. After the scientific results are returned to ESA, the detailed information about these stars are released to scientists across the world.
Now that we've released the first data, we continue with the processing, but actually the processing for the second data release already started a number of months ago. So we do these activities in parallel.
The full map of 1 billion stars with distances and motions will be released towards the end of 2017. But the astronomical community will be delighted with the first batch of 2 million stars, in the knowledge that there is far more to come. Galaxies come in all shapes and sizes, and while several 100 billion galaxies are estimated to be in our universe, only one of them is home to Earth. Our planet and its sun lies in one of the Milky Way's spiral arms, but while special to us, our sun is just one of around 100 billion other stars in the galaxy. So in order to better understand the Milky Way, its past and its future, the Gaia spacecraft has been surveying the skies since 2014, and it will make up to 70 observations on average for each star over the 5-year mission. The first data release in 2016 charted 1 billion stars, but only included the distance and motions for 2 million. The second release has now updated this to an extraordinary 1.7 billion, and with greater accuracy, including the distance and motions for nearly all the surveyed stars. This new image, showing the distribution of stars in the Milky Way, represents 22 months of observations. The dark areas are not empty. They contain interstellar gas and dust, and are often regions where new stars are forming. This stunning new image was produced by recording the colour from stars and combining it with their overall brightness. We now know the position and brightness of 1.7 billion stars. Importantly, as well as the colour, we also know the distance and proper motion of 1.3 billion stars, plus the surface temperature of 161 million, the radius and luminosity of 77 million, and the radial velocity of 7 million stars.
The most eagerly awaited result from Gaia are so-called parallaxes, which is the measurement which gives a handle to the distance of the stars. And this is a very tough measurement to be done. And we have known since Hipparcos, the previous ESA mission, distances to about 100,000 stars. And Gaia is going to increase that number to above 1 billion. So that is a real revolution.
Obtaining the parallax measurement involved determining the apparent motion of the star by using 2 different vantage points along Earth's orbit around the Sun, and separating it from the star's true motion through the galaxy. Closer to home, Gaia observed 14,000 known solar system objects too, mainly asteroids, and far away it measured the positions of distant quasars to create a new cosmic reference system. The first data release already produced hundreds of scientific results, but for astronomers across the world, the best is yet to come.
The essential thing of the Gaia mission is that the surprises will come later, because we make the catalogue, and it is the scientists in the community who are going to utilize it and give the scientific surprises to us.
The Gaia mission is expected to be extended to 2020, which means not only cataloguing more stars, but also examining possible exoplanets around them, and even more surprises.